I will now talk about a second example for illustrating dynamic programming. And in this case, I want to revisit a problem we saw in the context of greedy algorithms, but slightly modified. So I remind you of the compatible intervals problem. The compatible intervals problem, we had a set of intervals, each one of them with start and finish time, and we wanted to take the largest number of possible intervals that don't overlap. And we saw a greedy algorithm for that. If you sort them by the finish time and you take them based on the finish time such that they no two overlap, then you will get an optimal solution. So now we have slightly different version of it, which is the weighted compatible intervals problem. So what is this problem here? The input is a set of weighted intervals. So interval I, such that interval I is given by the start of that interval, the finish time of that interval, and the weight of that interval. Okay, so we have Si, Fi, Wi, and we know what compatibility means, that two intervals are compatible if they don't overlap. Okay, the finish time of one is before the start time of the other. Okay, and what's the output here? We want to find now not the maximum number of mutually compatible intervals, but we want to find the maximum weight of mutually compatible intervals. Okay, so for example, when we had this case where, suppose we look at this case here, and so suppose these are the intervals and I'm showing you their overlap and so on. If I were going after the compatible intervals problem, I want the solution should have the three short intervals. But imagine that the weights of these intervals, the weight of the first short one is 5, the weight of the second is 10, and the weight of the third is 10 as well. But the weight of the longer interval is 100. So for the compatible intervals problem, we want the three short intervals because we are maximizing the number of compatible intervals. For the weighted compatible intervals, we are interested in the weight, the total weight of the compatible intervals. So in this case, the solution to this problem should be this one. Okay, solution to this problem should be this one. Now, if you look at this example I just gave here, you will immediately see that the greedy algorithm that worked before doesn't work anymore. Our greedy algorithm, I remind you, our greedy algorithm for this problem that worked is that sort the interval by their finishing time. So the one that finishes first, then the one that finishes second, and so on, and then take compatible intervals based on that order. If I go by this, then this one here, this is the interval that finishes first. If I go with this one, then my solution will end up choosing these three intervals. But this is not the one I want here. Okay, so the greedy algorithm of take by the finish time is not going to work, and the other ones, of course, are not going to work. Right, the start, go with the start or the length of the interval. So greedy algorithm is not going to work here, and this is a problem now that is amenable to recursive reasoning and the dynamic programming implementation. Okay, so I want you to pay close attention to some definitions I will make here, and let us now think about them. That we will have, go back to here. So we have n intervals and their finish times are f1, think about them, they are sorted, that one finishes before the second, before the third, all the way before the nth interval. I will make a definition now. Okay, so I will define for each interval, for interval I will define Pi to be the largest interval index smaller than I, largest interval index j smaller than I, such that intervals I and j are compatible. Okay, so we have sorted these intervals, f1, f1 smaller than f2, smaller than f3, and so on. So imagine I'm asking you, what is the p of 5? Okay, p of 5 is, of the intervals 1, 2, 3, 4, which one of them is compatible? And let's take the index, the highest index of the compatible ones. So imagine that this is interval 5. Imagine that this is interval 5 here. And this is 4, like this. And this is 3, like this. And then we have 2 here. And we have 1. So suppose these are the intervals. Notice that, again, they are sorted by their finish time. 1 finishes before 2, 3, and 4, 5. If I look at this and I look at interval 5 and I want to compute P of 5, I'm saying of the 4 intervals before it, what is the highest index of the one that is compatible with it? 4 is not compatible with it, so I cannot take 4. 3 is not compatible with it, I cannot take 3. 2 is compatible, therefore P of 5 is 2. Okay? So P of I is the largest interval j, index j, that's smaller than I, j is smaller than I, such that intervals I and j are compatible. And now we need to think about the optimal solution for this problem, and we are going to look at it recursively, and we will almost always define the optimal solution. Okay, so I will denote by opt the optimal solution here, optimal of I. So what is optimal of I? Opt of I. This is the value of the optimal solution. This is the value, okay, which is the total sum of the weights of the optimal solution to the problem on the intervals 1, 2, all the way to I. Okay, please look at this carefully. I'm defining opt of I is the value of the optimal solution on the intervals from 1 to I. Okay, if we define it like this, then the solution to the problem we are interested in is going to be in opt of n, right? So opt of n is going to be the value of the optimal solution on the interval from 1 to n, which is really what we want to solve. So we now want to think about it recursively. I want to find opt of n in terms of opt of smaller values of n, okay? And we want to define it for, we are going to go through, we have these intervals sorted by finish time from 1, 2, 3, all the way to n. We want to compute opt of I. So now let's look at this carefully here, and let's reason about it. So I have the intervals here, 1, 2, 3, all the way to I minus 1 and to I. Okay, so I want to find the solution for these intervals. And I'm going to ask this question here about I. Remember that we need the intervals to be compatible. I cannot just maximize the weight. I have to take also the intervals to be compatible. Now, remember that we had defined something that is P of I here. So we have an element here that is P of I. P of I is the largest index of an interval that is compatible with I. Okay, the largest index, smaller than I, that is compatible with I. So these intervals 1, 2, 3 all the way to P of I, these are compatible with I. What does this mean about these ones here from P of I plus 1, P of I plus 1 all the way to I minus 1, okay? These intervals cannot be in the same solution that includes I. I is not compatible with interval I minus 1. It is not compatible with I minus 2. It is not compatible with any of the intervals all the way down to P of I plus 1. So if I is part of the solution, then that if I is part of the solution, I is part of the solution, then it must be that it is the value, the weight of I plus whatever that optimal solution all the way to P of I we had. So what was the optimal solution we obtained from this part? Add to it W of I. This will be the weight of a solution that involves I. Now, does I have to be a part of the optimal solution? The answer is no. So I might not be part of the solution, is not part of the solution. Okay, so here we had opt of I equal Wi plus whatever opt of P of I. If I is not part of the solution, then opt of I is just opt of I minus 1. It's just we are ignoring the interval I. Okay, so again, reason about this problem recursively as follows. Ask yourself about interval I. Say, does it have to be part of the solution? The answer cannot be yes, cannot be no. It could be either yes or no, and we have to evaluate both possibilities and take the best. So if I is part of the solution, then the solution has the weight of I plus the weight of the solution that involves intervals from 1 all the way to P of I. If I is not part of the solution, then the solution is the weight of the solution on the intervals from 1 to I minus 1. I is completely ignored. Which one do we take? Well, we take the best of these. So opt of I is really the max of these two values. Opt of I minus 1 or Wi plus opt of P of I. This is what we do. Okay? Now, if I is 0, we can set opt of I to 0. Okay? So this is really the crucial formula that we always need to think about when we are coming up with dynamic programming, because this is the recursive formula. So I thought recursively about the problem. I want to find the solution that involves intervals from 1 to I. By involve intervals from 1 to I, I'm talking about it's a subset of these intervals, but I am ignoring, when I'm computing opt of I am ignoring intervals I plus 1, I plus 2, all the way to n. I'm concerning myself with the prefix of this sequence all the way from 1 to I. And I ask myself, is I part of the solution? I say, okay, it might be or it might not be. If it is, then its weight has to be included, and then let me add it to the weight of the optimal solution involving intervals that are compatible with I, and that will be opt of P of I. If it is not, if we know I is not part of the solution, then opt of I is nothing but opt of I minus 1, and we take the max of these two. Okay? Now, this is done. I mean, this is the solution to the problem. Now, this opt of I, the way I wrote it here, if you think about opt as the name of a function, then you have a recursive algorithm here. So if I turn this into a recursive algorithm, this is opt of n, for example, and I say if n equal 0, then return 0, else. Now again, we do this recursive formula since it is now the I is really n, so now we return the maximum of the weight of n plus opt of P of n, or opt of n minus 1. Okay, so notice that these are two recursive calls. So you call opt on n minus 1, you call opt on P of n, and you return the maximum between opt of n minus 1 and opt of P of n plus W of n. Okay, again, here at the beginning of this algorithm, we are assuming the intervals are sorted, f1 smaller than f2 and so on, and we assume this P of I, P of 1, P of 2, P of 3, all the way to P of n, these values here have been computed. So this is a recursive algorithm. Again, if you evaluate it, you will see this is exponential. Okay, this algorithm is exponential, and it's going to be problematic because of lots of overlapping problems. If you want to verify that, again, take opt of 10 and just evaluate. You're going to see opt of 10 and opt of 9, and you'll see multiple opt of the same value multiple times that the recursive algorithm in this kind of implementation cannot avoid, and that's going to cause problems. So dynamic programming says instead of computing opt as a function and calling opt on n minus 1 and P of n, turn opt, this function, turn it into an array in this case, okay? So this is the recursive algorithm, and it is exponential, okay? It's not good. If I want to turn this into dynamic programming, now we can, again, we always initialize, suppose I want to define this matrix A of I, which is basically opt of I, okay? The value of the optimal solution on the intervals from 1 to I. And now I start filling this matrix here for I equal 1 to n. I can say A of I, we can initialize it to empty. Okay, we don't put anything in it for now. And we initialize A of 0 to 0. Okay, so A of 0 is 0. When you don't involve any interval, the total weight is 0. So now we go through this calculation here of the matrix, or this array here, and we say if A of I is empty, then A of I, based on that recursive formula, is nothing but the maximum of A of I minus 1. This is the value that basically says I is not part of the solution. Or we have the A of P of I plus W of I. Okay, now I want to actually illustrate something here that I want you to see that I can implement. So I didn't put the for loop or anything here, right? I didn't put the for loop. But if you think about it, you can go from I equal 1 to 2 to 3 and so on, right? I mean, this if statement has to be inside the loop. But I want to show you that actually we can now implement this recursively, but in an efficient recursion, okay? So I want you to think about this carefully here. Not every recursive implementation is bad, okay? This is why I kept repeating that the recursive implementation, the way I showed, is bad, okay? This recursive implementation here, opt of n minus 1 and opt of P of n, this is problematic. Now, if we think about it carefully, we can implement this in a more careful way. So if we think about it as using this array AI, and then I talk about, for example, still it is a recursive implementation, okay? Recursive function, okay? Recursive function. I don't want to give it now a name. And I want to compute n. If you think about this, now we say here is that if A of n is empty, then let's compute A of n. Okay, A of n is the max of w of n plus, now let's call the function recursively on p of n, and the function recursively on n minus 1. But it's very important to read this carefully and see what's happening here. This is a recursive function that's called on n, and I want you to see what's the difference between this and the previous one. This function is going to go through this element n. So suppose we are going to compute it on n equal 20. So it's going to go for 20 here and say if a20 is empty, then a20 is going to be the maximum of these two values. But look at this. This is the key issue here. This is the key issue. That if an is empty, then do the calculation. So when you call this function recursively the next time, if the values have been computed, they are not going to be computed again. Okay? So every time they are computed, now an is no longer empty. And that's when the first time you come to calculate a of I is empty, so it's going to be calculated. The second time as a of I is going to be needed, a of I is not empty, therefore we just use the value from there. Okay? So if a of n is empty, we do this else. Here we return, okay, we return a of n. Now remember that outside this recursive function, the array a was initialized to a of 0 is 0. So here the initialization, a of 0 is 0. And a of I is empty for I equal 1 to n, okay? So this is really the algorithm. We initialize the a to be empty for everything except for 0. A of 0 is 0. Then we call this function recursively. This recursion is different from the previous recursive algorithm I wrote, because this time, before we call the function recursively, we ask if it's been computed. And this is what if a of n is empty. Okay? So this is a recursive algorithm or a recursive implementation that is making use of values that we stored. This notion here is what we call also memoization. Okay? Memoization. So when we talk about dynamic programming, or memoization in this case here, we don't want to have the most straightforward implementation of the recursive algorithm that doesn't avoid recalculating overlapping solutions. No, we are talking now about solutions that let's identify where the overlaps happen, compute the solution on these overlapping segments once. Every time we need it, we make use of the value that was already stored. Okay? So this is the solution here to this problem. Now, this algorithm, if you think about it, the algorithm here, of course, the sorting of the finish times is n log n. Computing the p of I is going to be O of n, given that the intervals are sorted. And then this function, this recursive function here that's written on this screen, is O of n. So this algorithm, the full algorithm, end up taking O of n log n. It's really dominated by the time for sorting at the beginning. Okay? Now, are we done? Is this the solution? The answer is no, because what does this algorithm return? This algorithm returns a value, a numeric value, right? It returns the weight of the weight of the optimal solution here. But suppose you want the intervals themselves. Remember that in our greedy algorithm before, the output was a set of intervals. Here, I'm not giving you a set of intervals. I'm telling you that the weight of the optimal solution is 500. But you might come back to me and say, okay, that's the weight. But what are the intervals themselves that are compatible and whose sum of weights is 500? How do I get that? Okay, so to get that, we have to use a technique that we call traceback. So how do we trace back? I'm not gonna write the pseudocode here, but let's illustrate it to clarify things. Remember that when we did opt of n, okay, I will use opt now, or okay, actually let me not use opt, let me use a of n. When I did a of n, this is the maximum of a of n minus 1 and W of n plus A of P of n, right? This is the formula. So now we have the intervals given to us. I'm gonna put them like this here as if they are not overlapping. So this is interval 1, 2, 3, all the way to n minus 1, n to n. To get the set of intervals, we start with this one here. We say, is this interval, so now we are gonna go from the nth interval, and I'm gonna go left all the way to 1, and I'm gonna start assembling the set of intervals. I'm gonna give you back the set of intervals, and I'm gonna put the indices of the intervals here. So I ask, is n part of that optimal solution? Well, it's easy to check because I have already computed this matrix A of n. So when I computed A of n, imagine that A of n was 500 again. This 500 is the max of two values, one from here, one from here, right? So imagine that this was 500 and this was 492. If this is the case, that A of n is 500, and these two values are 500 and 492, it means A of n equals A of n minus 1. This corresponds to the case where n is not part of the solution. So n is not part of the solution, I don't add it to x. So now I go to n minus 1. Imagine that, so A of n minus 1 is 500, and it is the max of A of n minus 2, and, W of n minus 1, plus A of P of n minus 1. Imagine now that this is the max here of this is 500 now, and this is 390. Then A of n minus 1, or n minus 1 is part of the solution. So now I say interval n minus 1 is part of the solution, and so on. So basically, we go back through this matrix. So if I want to write it in, so I can basically say for I equal n to 1. So I'm going all the way from the back of the array to the all the way to the beginning. I go from n to 1. If AI equals A of I minus 1, okay, so it basically means A of I is the max came from A of I minus 1, then we don't add I to the solution, okay? Nothing here. Basically, we don't add interval I, else add interval I to the solution. Okay, so this is really the algorithm. It's called trace back because I am now tracing the array back from n to all the way to 1, and I'm asking at every point when I'm looking at entry I, did the value at entry I in A come from I minus 1? If it came, it means interval I is not part of the solution, otherwise I is part of the solution. The very last point here, you might ask, what if this max is coming from, so what if A of I equals 500 and this 500 was the max and both values here were 500, okay? Well, in that case, you just take one of them arbitrarily. This is saying that there's an optimal solution that involves I, and there's another optimal solution that doesn't involve I. You can make your choice, okay? So you can either take I or not take I. It will give you two different solutions, but both of them will have the same optimal value of 500, okay? So to summarize this point here or this video about the weighted compatible intervals, we have a set of intervals, and each one of them has the start time, the finish time, and its weight. We want to find a maximum weight set of intervals that are mutually disjoint or non-overlapping. Greedy algorithm doesn't work, as I said. I showed an example for that. The greedy algorithm I showed doesn't work, by taking by finish time. Then we went to this recursive solution where we defined opt of j is either j is part of the solution, which means opt of j equals w of j plus opt of p of j, or opt j is not part of the solution where opt of j then is opt of j minus 1. Then the direct implementation of that algorithm, recursive algorithm, will give us an exponential running time. The dynamic programming here, or the memoization in this case, would say, let us actually start from 0 and store the value whenever we compute it. So opt of I is already computed and stored in A of I. And now next time we need to make use of A of I, we want to compute opt of I. If A of I has been computed, just look it up from the array in one operation and make use of it. And this algorithm now drops down to O of n. We have the n log n for the sorting at the beginning, but the work of the dynamic programming after the sorting is O of n.